Then we come to the last section of this educational symposium, which will be from Fernando Calamante, who came all the way from Australia to us in order to tell us about how to combine functional connectivity and structural connectivity.
Okay, thanks, and thank you for staying till the end. We're going to talk a bit about how we can combine structural and functional information. So we saw that MRI is very powerful for measuring structural connectivity. That's what we saw in many of the talks before. But it's also very powerful to study functional connectivity. There are various fMRI methods that one can use. ASL, ball, Vasel, ball by far is more commonly used. And as we saw, structural connectivity provides, if you want, the cabling for these connections, for this communication. And functional connectivity, what we look is at the coherence or synchronization of the signal that we measure with these fMRI methods between different populations of neurons. And there has been several studies suggesting that the functional connectivity is, in parts, facilitated by structural connectivity. And this study by Chris Honey has been very, very influential, where they show that there is some degree of correspondence between the structural connectivity and the functional connectivity. And so if we look a little bit more about it in detail, we can see that on the left side is a parcellation. In this case, was a parcellation with very fine regions, about 1,000 regions. And they look at the correlation between, in the y-axis, the functional connectivity, and in the x-axis, the structural connectivity. And they found that there was a significant correlation there. It's important to note that it's only looking at the nodes that they had a connection, a direct path, so only looking at those ones that they did have a direct structural link. And there is this link between the two, or correlation between the two. And also looking at reproducibility, what they also found is they did a test-retest of the data. And when you plot in one axis and the other the functional connectivity of the first scan and the second scan, you have here on the left is for a single subject, on the right for the average data. And what they found is that the black dots are the ones that they have, again, this direct link. The blue ones are the ones that they didn't have the direct link. And they found that they were much more reproducible if there was a direct path. So the functional connectivity is much more stable than measurement if there is a direct path. So as I said, it is, as they show and other people showed, there is a likely link between one and the other. But obviously, as we saw also from the data, this is not a one-to-one mapping. It's much more complex the situation because we have the contribution from the indirect paths and also the very important contribution from network dynamics. The functional connectivity can change in the order of, let's say, minutes, while structural connectivity doesn't. So we can't just say that one says the same thing as the other, but there is obviously an influence. And there was a nice analogy by a paper by Nakagawa recently where it kind of linked the connectome to a road system. And they said, well, the functional connectivity, we're looking about the traffic volume. The structural connectivity gives some information about the street size and the roads. So they obviously are linked to each other, but the dependencies is more also affected by the dynamics of the population at various times. So, you have the areas like the traffic jams in rush hour and things like that. So the street size and the street positions have some influence on how much traffic you get, but it's not fully determined the system. And typically, most often these two aspects, the structure and the functional, are considered independently from each other. But there has been in recent years a lot of push to try to combine it and look them together because obviously one gets much more information by looking at both aspects together. And so the way that people have been doing it is there are various ways to combine them. By far, again, the most common one is to treat each of them independently, calculate them, and then to combine them either quantitatively or qualitatively as a post-hoc type of analysis. Once you get the results, let's say that you get a tractogram or an FA map or something like that, and then an fMRI result or functional connectivity, and then you look at both of them. This pathway goes to this region and so on. Or you can try to correlate the results. Again, you can get some DTI measurement, things like that, see where it is in a pathology, get some functional connectivity measurement or fMRI measurement and see where it is and correlate it voxel by voxel. Or you can use one guide the other one. So, for example, you can use a functional connectivity result to use those as seed and target regions for your fiber tracking. Or conversely, use the results of the fiber tracking to know where you should seed the functional connectivity data to do seed-based connectivity. And also to use the functional connectivity to model the structural connectivity. And again, coming back to the study from Chris Honey, other people have done it too, but this is the most influential. So very basically what this modeling works is you get your tractogram. From the tractogram and give a parcellation, you generate your connectivity matrix, as we saw in a previous earlier today. Then from that one and some modeling, the most common model to use is the neural mass model, and also with a modified balloon model to generate the ball data. You can simulate what that data would have produced as functional connectivity matrix. And then you can also, in those subjects, measure actual fMRI data, do the same parcellation, calculate your functional connectivity empirically, and then relate one from each other, and try to understand if one can inform the other or guide the other. And what they found, again, plotted in the y-axis is the simulated functional connectivity, and the x-axis is the empirical functional connectivity, and they found a high correlation. Once again, this is only for looking at the edges that they had a direct link, direct structural connectivity. So once again, what they concluded is that with this modeling confirms that to some extent structural connectivity partially predicts or informs what functional connectivity can be. More recently, there has been also a lot of push on try to do this at a much earlier stage, to try to do not each of them study separately and link them later on in analysis, but try to put them together early on from the beginning to see if one can inform the other and get more robust result or a better integration of the information that we have. So there are various ways to do that. For example, the group from Vince Callum has been doing a lot of this work, and they've been using these data-driven approaches. For example, this one is a multimodal canonical correlation analysis followed by a joint independent component analysis. So schematically, how it works is you get your fMRI data and your diffusion data. You do your MCCA analysis, and you have to choose some features to be able to do this MCCA analysis. So for example, for the functional data, you can use your results from a typical GLM study, so your network of activation maps. For the diffusion data, they typically use either the fractional isotropy or one of the, let's say, the axial diffusivity or the ADC map, one feature of the DTI data, the tensor. And then once you get your components from the MCC analysis, you put them together and you follow that with a joint ICA analysis. So you get a set of components, spatial and functional components, that they are related to each other. So for example, in this study in neuroimage, this is one of the components that they found. On the left is the functional component. This is from an auditory task, fMRI task. And on the right is the diffusion component, the structural component based on the fractional isotropy. And then they can go a bit farther and say, well, depending on which pathways are affected here, they can start building some models of, depending on how the frontal lobe is connected to a temporal lobe and to the occipital lobe, and which areas are affected when they compare the groups of patients that they were comparing here. One of the limitations of this, as we saw in previous talks, is that just looking at a particular feature of the diffusion tensor image contains very limited information that we have available from, for example, the whole diffusion MRI data and the tractogram. So from that point of view, we are throwing away in some way a lot of the information. But still, you can get very useful information. They have done very nice clinical studies on this. Another approach is by Baumann et al., where they define this anatomically weighted functional connectivity. So the way that it works is that you define a functional connectivity distance. The distance is effectively the inverse as the connectivity. So areas of high connectivity have low distance, areas of low connectivity have high distance. But what they do is they scale this distance based on the structural connectivity information. This is an ad hoc scaling. So graphically, how this works is you get your fMRI data on the top, your tractogram or diffusion data on the bottom. For each of them, you can relate, for a given set of regions, a connectivity matrix, the top one for the function, the bottom one for the structural. And what they do is they combine both of them into a single connectivity matrix that is what they call the anatomically weighted functional connectivity. And without going into detail about how it's done, you can see that the distance weighting has the, let me see if I can use from here. So the weighted distance has the functional connectivity distance that was that one, and the structural connectivity information. So the scale that, where this parameter is one, you can choose to attenuate more or less the contribution from structural connectivity. So once you have that, you have one single connectivity metric that has both the structural and functional connectivity information, and then you can do analysis, parcellations or connectome type of analysis and things like that. Another way that various people have been doing is putting this into a Bayesian framework and, for example, use the structural connectivity as prior for the functional connectivity calculation. And, for example, here is a recent study in Frontiers of Computational Neuroscience. So the approach that we chose to do is known as track-weighted imaging, and I'm going to use a couple of slides to explain how it works. So the track-weighted image is a method we proposed a few years ago to combine a tractogram, so the diffusion part of the structural connectivity side, with any particular image. So here, this map A is an image, and in particular, this one is a PET image, so it doesn't even have to be an MRI image. And the idea is that you combine them to generate a track-weighted version of the map A. So schematically, how this works is like this. You take your tractogram, and let's say that you want to know what's the information of this track-weighted image in that voxel highlighted there. I don't know if you can see the voxel. Where is it? Here. Somewhere there, I think it is. So you go and look at all the tracks or streamlines that go through that place. Let's say that this is schematically one of those streamlines. Then you overlay it. You assign to each streamline a given weighting, and that weighting is based on that map A that you're trying to do track-weighted. And there are obviously many, many choices you can do. It is very flexible, so you can choose, for example, go for the mean value, the standard deviation value, or whatever along that pathway. You can choose also how much stent. You can do the whole streamline, or you can do a given neighborhood information around that streamline. But whatever it is the location of that streamline in that map. And then you do that weighting for each of the streamlines going through that place. And then again, it's very flexible in how you can choose to combine them. You can do the mean of all those weighting. You can do the standard deviation of those weightings. You can also do it as keep the high order visualization, so you keep it all the fibers in separate place and things like that. But the bottom line is that you can map information of the map A to each streamline and then combine them into a new image. And it has super resolution properties in the sense that you can generate an image that is higher resolution than the data that you started with. And I always get asked why you can do this. So hopefully this slide, I'm trying to explain that. So if you focus on this area here, where you have the corpus callosum and the cingulum crossing, so there will be the corpus callosum going somewhere here, and the cingulum going in and out of the plane somewhere here. This is diffusion data acquired at 2.3 millimeter resolution. You put your fiber orientation distributions like that, and then you can see there, let's focus in that voxel there. And as I said, you have the cingulum bundle going in and out, the corpus callosum going diagonal. And at that point, there is absolutely no information within the voxel where those bundles are. What you know is there are two bundles, but you don't know where it is. This can be solved once you put the tracks. So if you do whole brain fiber tracking, you do a tractogram, and you overlay them there, and you just look at the tracks. You forget about the voxel size and the FODs. Let's zoom up again. Now you can start to see that the tracks provide brought up information from outside the voxel to within the voxel. So if we compare it to what we had from the data that we acquired, on the left, we didn't know where those bundles were. On the right, we know where the bundles are because the tracks tell us that the bottom left corner is mainly the cingulum, and here is the corpus callosum. Yeah, the corpus callosum. So in some way, the tracks provide information to get subvoxel information, localization. So that's how we are able to get the super resolution. So we do that, then we put a mesh of the resolution that we want, for example, a tenth on each dimension, and then we calculate our information in each of those subvoxels and get our higher resolution image. So let's go back to how we combine these for the particular case of functional connectivity. So the bit that I'm going to describe for the rest of the talk is how we is a specific case of track-weighted image that is for the case where the map A is functional data. So there are two ways that we can combine these. What we do is we get our diffusion MRI data, our ball data for each subject. With the diffusion data, we do our tractogram. For ball data, we do our functional network. As I'll show, there will be many ways that we can do this. And then we can combine them into a track-weighted functional map. The two ways that we can do this is by using a specific network, and this is the example that I've been just showing. So we calculate from the ball data a given network, and I'll show an example in the next slide. Or the other way is without having to assume any specific networks. This is a bit more general. The idea is we skip this step altogether and we use the actual ball data straight combined with the tractogram to generate our track-weighted map. So let's go to the first case, that is with a specific network, using this functional network here. How do we do it? So this is shown in this particular example for the default network here. So you choose a particular network. Here is the default network. You look at all the tracks for that subject, and once again, for each track, you're going to assign a given weighting. So, for example, let's look at one of these tracks, one of the tracks in the singulum, connecting these nodes of the default network. You assign a particular weighting, and the way we chose here was a very simple way. We just sum the values of the functional network along the pathway and assign that weighting to the track. So in some way, you're mapping information of the functional data into each of the pathways. Then you do that for all the pathways that you have there. So each of them would have a different weighting given by the functional connectivity. And then overlay the fine grid, as I said. And on each voxel of that grid, you assign an intensity. And again, in this case, the one we chose was very simple. Just get the average of all those weightings. And you get a map like this. So the intensity of the map is the mean functional connectivity value of all the pathways of the tracks transversing a given voxel. So if I put on the right, just because I covered it with all this side here, so that was our original functional connectivity network. That's the track-weighted functional connectivity network. So what you can see is, in some ways, the track-weighted functional connectivity is propagating information of this one along the pathways, and the intensity is related to this function information. So you map the functional data into the pathways, and you get information here both about the structural and the functional within a single image. As I said, this is for the case where you have a specific network, but you don't have to have this just for one network. So you can do a very simple thing, like, for example, taking your fMRI data, put into an independent component analysis, and getting all your different typical network, like, for example, the default mode network, which I have attention network, visual network, and sensory motor network. And there will be many others when you get with the ICA. And each of these, one at a time, related with the tractogram, and get the track-weighted functional connectivity of each of them for one tractogram, just to show the anatomy, is the track density image on the left. So you can see, for example, here is a very similar, it just is now in grayscale, but it's the same data as I showed before. So that would be the default mode network we've been looking at. The attention network, so we can see here, the superior is primarily superior longitudinal fascicular, but again, it's propagating information of that one in the pathways. In the visual, we have the optic radiations, again, propagating information. And here we have the corpus callosum and the corticospinal tract. So once again, you can see that what it does is it propagates information, and you end up with an image that has both structural and functional connectivity information in a single image. Any type of image can be used. All I've been showing so far is functional connectivity, but for example, you can take an fMRI data. This is a temporal lobe epilepsy patient with language fMRI. So it's a task where you, the OLR task, orthographic lexical retrieval. So you show the subject one letter, and the subject has to think as many words as possible with that letter, and so on. That's the task, and then the rest is fixating to something. And then you combine with the tractogram, and you end up with the track-weighted fMRI data, where you see, for example, the fasciculus, the Broca's and Wernicke's area. And again, this one has propagating the information of that one along the pathway, and it has both the structure and the functional information into one map. You can use, for example, this is a patient with epilepsy patient with local cortical dysplasia. It was somewhere around this, underneath that blob there. And this is on the left, you have the result from EEG fMRI. Again, you can combine it with tracking the tractogram and generate the track-weighted EEG fMRI, showing the full network, both the structure and functional information of how they mapping the functional data into the structural data. It has been used a lot, this type of similar approaches, as a more seed target approach, where you take your network. I think I may have it in the next slide, yeah. So you take, let's say, the default mode network, where you have the axials, coronals, and sagittal, and then you take those as seed and target regions, and you look at all the pathways connecting that one. For example, these are the track that you would get by tract editing that data. So every pathway from the tractogram that connects these nodes. And then you would measure things from that one. The advantage of the approach that has been shown compared to this type of approach, of seed target approach, is that it's more inclusive. And this is illustrated here. So we have here, again, a track-weighted functional connectivity of the deformable network. The top row are 4 slices, axial slices. Here are 4 sagittal slices. And again, for anatomical reference, I have the track density image on the bottom. And if you look at this area here, sorry, it's hard for me to see from here. I'm trying to see what is there and then see where I point. These areas here, you see, goes down from the precuneus posterior cortex all the way to the mesial temporal lobe. And it's not an area that appeared in the, it didn't survive our thresholding in the deformable network, but it's an area that has been shown by many to be part of the deformable network. So this is an area that if we were using seed and target type of analysis, combining structure and function information, you would have lost it altogether. But here, given it's a strong connection to the precuneus or posterior cingulate cortex, is an area that is well represented and is going to be present in this type of whole brain tracking approaches. So it connects through a cingulum and the hippocampal branch of the cingulum. So that covers the first part of the track-weighted functional connectivity, where you have to pre-specify the network that you want to focus. The second case I'm going to show you is when you can do it more generally. You're going to look at the whole brain without having to look at a specific network. So schematically, how this works is as follows. Let's say that we have this data, and we are looking at that voxel there. So once again, what we're going to look is at all the streamlines going through that voxel. Let's say that we found that's one of the ones we have. We look at the endpoints of the streamline, and we look at the ball data in those endpoints. And then we assign a weighting to that track. But now it's not related to a particular network, but it's more about the correlation between those ball data sets. So, for example, we use Pearson cross-correlation, and that's the weighting. Once again, we are mapping the correlation, the endpoints, the link between those two regions to the pathway that connects them. And in fact, we can do this time-dependently. It's becoming more and more popular to use this, for example, the sliding window. There are many ways to do it, but what we can do is a Pearson correlation in a particular sliding window, do this like this, so the weighting that we get will be time-dependent. We do that for all the streamlines going through that voxel. I'm showing here 5, but obviously there will be many, many more. And the map that we generate that to differentiate from the previous one we call here track-weighted dynamic functional connectivity, it's just calculating, for example, the average weighting of all those weightings for its streamlines. And for comparison, the data I'm going to be showing, we're going to also compare it to what I call here track-weighted static functional connectivity. That is exactly the same analysis as this one. This is dying. But without the sliding window. So using the whole data set as one single correlation. So if we look at a particular example here, we have on the left anatomical reference axial slice through the level of the basic ganglia. And this one here is tri-weighted static functional connectivity. So without the sliding window, correlation, the scaling is in correlation units. And this here, can we click on this image to start this movie, please? This is done, yeah. So you can see here how it's changing this map, these correlations during the sliding window changes, moves. And you can see, for example, if you focus into some of these ones, it's hard from here. But for example, somewhere here you would have the optic radiations. You can look at those ones, or the fornix there, or the cingulums going in and out there. You can see that lots and lots of change. It's changing a lot. It's not a constant value, but it's changing over time dynamically. So we can do this at each voxel, look at the temporal variations of these correlations, and summarize them in some way. The simpler way would be, for example, just look at the confidence interval and plot that at each voxel. So we have here is the confidence interval of those variations at each voxel, the temporal confidence interval. So if you see, for example, some areas that they change a lot, like the fornix, you can see here is high intensity, so it's a reddish. And if you look at the map that the movie is going, you can see how it changes from red to green to blue. Some other structures, like a cingulum going in and out of the brain, the optic radiations, even some subcortical regions like the ventrolateral nucleus of the thalamus, again changing quite a lot, and you can see in the movie too. And some areas that don't change much, like for example the tapetum and some other ones, that they are very stable over the window that we have. So in that way, what we generated now is a 4-dimensional data, so 3-dimensional space plus time, where we have both structural and functional connectivity within a single image. So we are mapping the functional data into the pathways, and that one is also has temporal information. So we can do is any typical analysis that you would do with fMRI, with ball data. For example, you can put into an independent component analysis. In this case, we use the FSL software, and find special components. So these are just a couple of those components. In each figure, on the left, we have the spatial component, and on the right of each of them is the time course associated with those components. So, for example, the one on the left is one where it's primarily on the cingulum bundle, connecting the precuneus posterior cortex with the medial prefrontal cortex, so two key nodes of the default mode network. And that temporal variation, I don't know, I think this is dying. That temporal variation there would be the temporal variation of the correlation between those two nodes. So as I said, we are mapping the information of the gray matter into the white matter. And the one on the right is the visual network. So we have the optic radiation. Okay, just hopefully you see it. The optic radiation connecting the lateral genicular nucleus with the primary visual cortex. And again, the time course that you see there will be the changes over time of the correlation between those two areas that we are mapping in that pathway. You can also use this information for certain applications. For example, here I'm going to show is, following what Alfred showed, is how we can use it for parcellation. So, for example, we can get all the components that we have. In this case, there were 60 components. I'm showing the example here for the corpus callosum. So if we choose a region in the mid-sagittal corpus callosum, as shown here at the top right, you can then automatically select from the components which of them have a certain, with a given threshold of intensity and extent of the cluster, components within this region. And in this particular case, 9 of the 60 had. And for one of the subjects, this is what you would get. So those 9 components there. You can do that for each subject, or you can do group ICA. And you get, now this is the result from the group analysis. And again, you can get a parcellation of the corpus callosum based on the structural and functional information and the temporal functional information. And parcellating the corpus callosum sometimes is a very hard thing to do because each streamline along the corpus callosum, if you move, let's say, from the right to the left, they are very, very similar in size, in shape, and they only change very gradually. So it's a very gentle, gradual change. So just trying to parcellate this on the shape of the curves is very, very, a very hard task. And as I said, this can be done in a data-driven way, and it doesn't rely on having to assume any parcellation of the cortical parcellation to then map this one. The data themselves find which is the parcellation that should be. And you can go a step further to say, well, once we have a parcellation of the white matter, we can map it and parcellate the cortex. So, for example, we can do tract editing to parcellate the gray matter. So what I mean by this is the standard tract editing approach. For example, we can take all the streamlines that we have in the corpus callosum, go to this image here and take one region at a time. The top right, take one region at a time. So, for example, the region, that one, I think it's number 31. I can't even see from here. The blue one or that color. And then you tract editing and select only the ones that go through that region and map it to that, assign it to that region, and you go one by one. And in that way, you can generate a mapping of the streamlines to each of those regions that you parcellated before, data-driven way. And can we press in that image on the right, on this one here? Yeah, that one. And then you can see here how, based on in the data-driven way, you can generate a cortical segregation based on the information from the structure and function connectivity. So let's go now into I've been showing all this without saying what data I use, how we calculate and all that. So the rest of the talk is going to be more about how in practice, how do we do this and what things you need to be careful with. So for data acquisition, our typical protocol that we use a 3 Tesla scanner. Ball data, there is nothing particular about that. It's a standard acquisition. For example, for the function connectivity data will be a GrainTech API, 3-second time resolution, let's say the 10 minutes run, but you could use a different one. One of the key things is that we have to have that data there. As we discussed, we need to correct for distortion. So we acquire just a couple of images at the beginning with reverse polarity of phase encoding to correct for distortion. Our diffusion protocol is a hardy data, so 60 directions, b-value is about 3,000, and the resolution, as I said, there 2.5 or so millimeters. And again, for this data, we also have to acquire a reference data to correct for distortions. And we also acquire a T1-weighted image of about a millimeter or so isotropic for segmentation and things like that. So data acquisition is nothing in particular different to what you would do. Data analysis, for the functional connectivity, the bold data analysis, again, is very standard things. We do distortion, motion correction, smoothing, detrending, filtering, and nuisance regression. In this particular study, we didn't use any, we didn't remove any of the physiological noise, but obviously that would be even more robust if you have any of the measurements that measure physiological noise and you do that as pre-processing. So nothing particularly special there. For diffusion, we do some of the typical processings. Also, we do by a field regression, correction to remove any signal intensity inhomogeneities. And then we do constrained spherical deconvolution to model the crossing fibers, probabilistic streamlines, at least 10 million tracks, if not more. And then we do that using the matrix software. For the track-weighted dynamic functional connectivity, the two things that you have to choose is what sliding window to use. And typically the papers that have been around, they would say a minute or so is a reasonable sliding window, but this is something that needs to be explored to see how it changes with sliding window. And again, since it's super resolution, you can also choose what particular resolution. We chose this one just because it's the anatomical image, but this is also a parameter that you can choose. So this is the bits that are the most important one. So things that you have to keep in mind. It was discussed by others in the past. In this session, if you're going to be combining two different types of images, they have to anatomically match. So we use distortion correction, as I mentioned, for both of them, phase encoded up and down reference data to correct. But if you don't have that or you're not going to do that, the minimum you need to do is to acquire both the diffusion data and the functional data with the same bandwidth per pixel of the PI, so at least they have the same level of distortions. It's not going to be as good as having distortion correction, but at least they're going to be matched, especially if you're going to be trying to assign the gray matter to the white matter, the functional data to the pathways. For the whole brain fiber tracking, this is something that also Maxime mentioned in his talk. It's very important to know what's going to happen with the tracks and points. And as he mentioned, there can be a lot of tracks that for many of the tracking algorithms, the endpoints are very badly defined. So you can have tracks that end in the middle of white matter or in CFSF, or the tracks cross the sulci. So for example, if you look at this area here, so this is a zoom. It's a zoom of that area. We can see here the fiber orientation distributions, and these are the tracks, and every red dot is an endpoint of one of those streamlines. And as you can see, I have to point here, there are lots and lots of these red dots in the middle of white matter, in the middle of CSF. And for example, if you look at this area here, you can see that a lot of these streamlines crossing sulci, and the same, if you look at any of these sulci, there are lots of streamlines crossing the sulci. So if you were to do a typical, let's say this is probabilistic streamlines, even with constrained spherical deconvolution, you get a lot of these tracks that are completely wrong. And if you're going to be trying to map functional information to the track, and the track ends in funny places or crosses sulci, you're going to be mapping the wrong information. So as Maxime mentioned, in particular, we use the anatomical constraint tracking method from a matrix that we developed. And in that case, what you get is now you're using the anatomical information to force the tracks to only retain the tracks that they end up on the interface between the gray and white matter or in subcortical gray matter. So you eliminate some of these issues, and you have well-defined endpoints. So in the situation is when you have well-defined endpoints, either use ACT or some other method to deal with this, you can do a very rigorous assignment of the functional connectivity to the pathways, and then you can use the endpoints. And that's, for example, what we use in the method I've been showing you. However, if you don't use this approach, and that was what happened in our earlier data that I showed for the track-weighted functional connectivity at the beginning, we didn't have ACT at the time. The endpoints are not very well defined, so you can't use that assignment. And so one way around to go this is to use your network, threshold the network, and then you use information by thresholding the network, all these bits that is in the middle, plays no role. So instead of just using the start and end point, you can use the whole pathway as information by removing, to some extent, the track length dependency by doing a thresholded network. So it's important, depending on which tracking you have, which of these variants of the track weighted you're going to be able to use reliably. From the track weighted functional connectivity, the key for both of them, the key thing is to choose, as I mentioned, the spatial resolution, the sliding window, what connectivity measure you use. We've been using the cross correlation, but other ones can be used. And one thing that we're currently working on and is a very active field in dynamic functional connectivity is what particular null model you're going to be using to test if this is just noise or is real dynamic information. So in discussion, these two methods, track-weighted functional connectivity and track-weighted dynamic functional connectivity, is a method to combine and provide some synergy of the structure and functional connectivity information. You can fuse them into either a 3D image or a 4-dimensional image, and they have super resolution properties. The track-weighted functional connectivity highlights information of the white matter for a given network, and it has is much more inclusive than seed and target approaches. I can skip that. That is summarizing what I said. And the track-weighted dynamic functional connectivity, the one I showed at the end, is a much more general method because you don't have to assume any particular network. It's a tool that can be used to study dynamic functional connectivity. And the key thing compared to other methods that they do is dynamic functional connectivity, we are now operating in white matter. So we are mapping the information of the white matter into the gray matter. And the information we look is at the pathways that connect those things. It helps to constrain the very large amount of data, so we don't have to look at the connectivity between every point to every other point. It's only every point at the corresponding track endpoint. And for parcellation, it's very strong because it lets you combine information for structural information, functional connectivity, and dynamic functional connectivity in one way to do particle correlation. Acknowledgement of people and funding. If you're interested in a postdoc, there are a couple of places in my lab, so get in touch with me. And the final thing is, Alex asked me to show this. The ISMRM is organizing a diffusion workshop in September. So there are lots of information you can check in the website and keep an eye for the deadlines for abstracts and registration. Thank you for your attention.
Thank you very much, Fernando, for this great talk. I think there are questions. So please step to the microphone. Yes, please.
Very beautiful work. I have, maybe this is too complicated a question, but so all the tracts are by nature monosynaptic, while as a lot of functional connectivity is probably polysynaptic. So what happens when you try to propagate a polysynaptic functional network onto your sort of, structural tracts? Does it propagate through or does it fail?
Yeah, so if I get it, stop me if I got the questions wrong. For example, one of the typical cases that we have is we know that in the thalamus, the connection should stop in the thalamus and start again synapse there.
Yeah,
but the tracking, what it does is it tends to then, most of the time, just track through those ones. Right. So in those cases, for example, with the ACT framework that we have that one, there is anatomical information, we are forcing the tracks to end up. So once they enter in the subcortical gray matter, they end there, and if you only synapse there. So if you use those cases, you wouldn't. That would be surviving that case. If you don't use those anatomical constraints, the likely thing is that the connection that you will be looking is if you are not at the direct connection, but the indirect connection, because you will be jumping one through the thalamus.
Right.
So depending on the tracking algorithm that you use is the thing that you would be looking at. Mm-hmm. But yeah, it's a very important. Yeah, it's a very good point. Yeah. Mm-hmm.
Cool.
Yes.
Hi, thanks for this great tool. My question has to do, it seems like the method is basically labeling the tracts based on the functional areas that they connect, but it does not guarantee that those tracts are really the functional pathways.
Yeah.
So my question is related to a couple of other methods that I've seen recently. One called functional DTI, and the other one that I saw a few months ago on a poster that recovered the functional value of the tracts from BOLD, so they could extract the arcuate fasciculus from BOLD data. So my question would be if you are aware of these methods, or what would be the relationship with your method, and what are your thoughts on this?
Yes, I would need a bit more information about those methods to know which ones you're talking about. But so the first point is, it is right. So we are not talking, when we see, let's say, in the formal network, and you saw the cingulum had high intensity or there was high correlation in those areas. It's obviously the correlation is not happening in the white matter. We're just using the white matter as a mapped information. So whatever you see in any white matter pathway, what you're actually seeing there is the connectivity of the gray matter regions that pathway connects. So it's purely, if you want a data reduction tool, that it lets you combine the structure and function information into one single image by only looking at direct connections. There are ways that we've been exploring. You can extend this to second-order connection and third-order connections, but at the moment, as I show you here, it's purely direct connections. So what you're looking is, in some ways, if you think of this room and you look at the, maybe everybody flew here. If you look at in the map of the flight path, essentially what you're looking is what is the movement of people, but not looking at the movement of people in the airports and the cities, but looking at the movement of people in the pathways. So you're assigning to whatever is happening in the cities, and that would be the nodes, to whatever you see in the pathways connecting those nodes. The other ones, I'm not sure which ones. The DTI, are you talking about the one Denis-Levian measure? Which one are you talking about?
I think it had been one 2008, one 2013 by Mandel or something. They were talking both about this functional DTI, FA changing across time during a task. And I don't know why those papers never had a follow-up. To me, as an outsider, initially it looked fantastic, but this idea of changing the FA in time was great, and it would have helped.
Yeah, so no, I mean, I'm not so familiar about those ones, but it would be definitely something very different because FA has a very, well, as we saw in many of the talks before, it has a very meaningful interpretation that is very complex, particularly in crossing fiber regions, and you wouldn't have the wealth of information that you can get from a tractogram. So yeah, but I'm not familiar about those particular methods.
Okay, last question.
This is slightly tangential question, but I was interested in your parcellation of the mid-sagittal corpus callosum. Does that parcellation correspond to postmortem assessments of axonal caliber or in vivo measurements using G ratio?
Yeah, so it's a great question. It's something we were trying to, because obviously how you validate that the parcellation you get is a correct one, and the reality is not possible with the in vivo data, with the human data. Potentially, if you were to do, the closest you can get is there is the great book for that one, Fiber Pathways of the Brain, is Pandya and I'm terrible at pronouncing those names, but that where you have track tracing and they have very similar, is in the monkey, very similar distribution, but it's a different species, a different method. So it's going to be a very tough thing to validate these things, just as validating any parcellation, just because there is no gold standard about how to do this. Maybe to doing some of the ex vivo method with track tracing might be the way to go, but yeah, that would be a whole project on its own and a huge, huge project. But it's an excellent point, yeah.
Is there a last short question, or?
Hi, thank you very much. Yes, in a way, it's somehow similar questions. I was wondering which meaning you give to this tract-weighted functional connectivity, like can relate to some microstructural property of the white matter. Is that related to some traffic on white matter, you think?
Yeah,
connections?
So at the moment we're using it as, apart from the example of parcellation, that is something very recent we are doing, so in some way that is very limited information we haven't really explored in detail. The previous track-weighted maps that we published now for a few years, you can think it more as a new image that you can start comparing patients and controls and things like that, or correlating to pathology and things like that. It's a new map that has, you can imagine that a change in structural connectivity or a change in functional connectivity could be picked up by those maps. So, for example, in those ones with epilepsy, you can consider that you have a group of patients with epilepsy, and that's what we're currently analyzing, but we haven't finished the analysis, so I can't show you here, is that. So you can test a group of patients with temporal lobe epilepsy, a group of control, and see if you pick up either the structural and functional changes based on these maps. The assignment is, I don't think that these maps are going to be saying what we're measuring is, axonal information or things like that. It's just a new way to combine both aspects of structural and functional connectivity in a single image that you can then do further analysis. As I say, it's like that. It's more a data reduction, as I said, method. You have tons of information in the tractogram, tons of information in the functional data, is a way to put them together into something, and then you can do subsequent analysis.
Okay, thank you, Fernando, and I want to thank you all the speakers which brought together this symposium for diffusion and integrating like these new aspects of quantitative MRI in this community. I want to thank you all for joining in the symposium. Please don't forget to give a positive mark in the evaluation